Hey everyone, and welcome. Today we are talking about something incredible, an invisible rule, a law of the universe that governs every single file we shrink, every video we stream, and every message we send. We're talking about the absolute speed limit of data itself, and it all comes from Shannon's source coding theorem. Let's dive in. So think about it for a second. You zip up a folder to email it, your phone compresses a photo before you send it, but how far can that go? Can you just keep compressing a file over and over again until it's, one byte? Or is there a hard wall you eventually hit, a point of no return? This question, it's right at the heart of our digital world, and today, we're going to solve it. All right, so here's our roadmap. First, we'll really dig into that big compression question. Then, we're going to uncover the secret ingredient behind it all, this amazing idea called entropy. From there, we'll reveal the actual speed limit for data, see how this wild theory turns into the real ones and zeros of code, and finally, we'll talk about why this limit is, no joke, one of the most important concepts of our time. Okay, let's jump right in. We're going to start with something we all pretty much take for granted, the everyday magic of making digital stuff smaller. I mean, it is everywhere. Without compression, streaming a movie would be a total buffering nightmare, and sending a high-res photo from your phone would take, forever. It's the silent engine running in the background of our digital lives, making everything fast and, possible. And even though it feels like magic, it's all grounded in some really serious mathematics. The guy who first laid it all out, who first stopped and asked, wait a minute, where does this stop? Was a genius named Claude Shannon. And he wasn't just being curious. He was looking for a universal law. To find that law, Shannon knew he needed a way to measure information itself. And that brings us to the key concept for this whole explainer. It's a powerful and honestly a really beautiful idea called Shannon entropy. Now, forget the complicated math for a second. At its heart, entropy is just a measure of surprise. That's it. If a message is totally predictable, it's got low entropy. If it's completely random and you have no idea what's coming next, it has high entropy. It's basically a way to put a number on the unknown. And this slide just makes it so clear, right? On the left, you've got A. There is zero surprise there. You know exactly what the next letter is going to be. That's super low entropy. But on the right, X, Q, J, Z, K, W, B, it's pure chaos. You have no clue what's next. That is high entropy. And here is the big takeaway, that predictability is the key to compression. I can describe the A sequence really easily, just say 7 A's. But that random mess of letters on the right, you have no choice but to list every single one. Data with less surprise, less information is just way easier to shrink. Okay, so now that we've got a handle on entropy as a measure of surprise, we can finally pull back the curtain on the speed limit that Shannon discovered. This is the big one, folks, the source coding theorem. And there it is. That's the law. It says you simply cannot compress your data using an average number of bits per symbol that's less than the source's entropy without losing something. This isn't a guideline or a best practice. It is a mathematical certainty. Just let that sink in for a moment. Entropy isn't just some abstract measurement. It is the limit. It is the fundamental floor, the rock bottom. You cannot go below it if you want to get your original data back perfectly. It is literally the speed of light for data compression. This chart just lays it all out. If your average number of bits per symbol, your code rate, is greater than the entropy, you're in the safe zone. That's the bar on the left. Your data is perfectly fine. But the second you try to get clever and go below that entropy limit, like the bar on the right, you basically fall off a cliff. Information loss becomes not just a risk, but a virtual certainty. So, how in the world did Shannon even prove this? Well, the logic is just so clever. Instead of trying to make a perfect code for every single possible message, he focused only on what he called typical sequences, the patterns that are overwhelmingly likely to actually happen. Think of it this way. In English, the sequence "the" is way more typical than XQJ. By building a code that's super efficient for all the common, typical stuff, you can win big because the weird, random sequences almost never show up anyway. Okay, so we've got this beautiful abstract speed limit, but what does that actually mean for the real world? How does this theory shape the actual ones and zeros that make up our files? See, this is the other side of Shannon's genius. He didn't just tell us what the limit was, he basically gave us a map for how to get there. His theory gives us concrete mathematical rules for how long our symbol codes, the strings of ones and zeros for each letter or pixel, actually need to be. Just look at this table. It's amazing. Shannon proved two things. First, that lower bound. The average length of your code can never be less than the entropy, hx. That's the hard limit, the floor we talked about. But then, and this is the incredible part, he proved the upper bound. He showed you can always create a code that's, on average, less than the entropy plus just one extra bit. It's like he said, here's the finish line. And by the way, I'm giving you a way to get ridiculously close to it. And that right there is the whole point. This isn't just some fuzzy theoretical idea. The absolute best compression you can ever hope to achieve is mathematically chained directly to the entropy of the thing you're trying to compress. Shannon proved this limit isn't just theoretical, it's actually achievable. So let's zoom out for the big finish. Why do we care so much about a theorem from way back in the mid-20th century? What is the real legacy of this single idea? Think about that year, 1948. The digital world we live in, it hasn't even been imagined yet. There are no zip files, no JPEGs, no internet to speak of. And in the middle of all that, Claude Shannon publishes this paper that lays down the fundamental laws that will govern all of it. I mean, the foresight is just mind-blowing. This theorem, it's not some dusty footnote in a textbook. It's a cornerstone of our reality. It literally established the laws of data compression. It underpins everything from zip files to your phone calls. But maybe the most profound thing it did was prove that something as abstract as information could be measured, quantified, and understood like any other physical property. It turned information into a science. And that kind of leaves us with one final big thought. We just learned there's a hard mathematical limit to how small you can make a file, and it just makes you wonder, what other invisible rules, what other fundamental laws are out there shaping the technology we use every single day? What are the other speed limits that we haven't even thought to look for yet?